Say again. We continue now. So there was some question. There were some questions. Yes. I think one is the error of this method is order delta t, the local error, to the fifth. And so when you integrate, the error along after the whole thing is delta t to the fourth. Because you do 1 over delta t steps. Of this method, imagine if this method, for this method, there were one parameter family. For this other method, there are many. So there are many, for instance, fourth order methods. This is most known, but there are many. Then there are 5, there are 8, there are 16, or whatever people have done it for different problems. And then there are the Taylor type methods, and there are many. There are maybe 200 methods implemented. So you can see them here, for instance. If you look in this page, you can check many methods. Which one to use? It depends on the problem. It depends how costly it is to evaluate f or the derivatives. Because if it is simple, you can use some Taylor's method. If you have conservative systems like orbits, then you want a method that doesn't have an amplification factor, so that you don't get, instead of an orbit, something which goes like this. If there is dissipation, you want some method that you might have method which have this amplification factor, but still, because of dissipation, it's not so bad. There are problems which are stiff. That is, the lambda is very big. And here the lambda, we meant the eigenvalues of the system when you linearize it at some point. And so there are many reasons to prefer one or other method. For instance, sometimes you have an equation which is like this: dy dt equals to some matrix over some epsilon y plus some other metric b, which is okay. So in that case, you might want to get some methods which are implicit for this part. We are going to show how to do that later on. You might want to use some implicit method for this part and some explicit, like Runge-Kutta method, for this part. So otherwise your delta t has to be much smaller than epsilon, right? So you might use methods where this thing is not present, so you don't have this problem. And there are many. Sometimes you use what are called embedded methods. Embedded methods are methods that, for instance, compute. They have a Runge-Kutta for fourth order and another for fifth order. but the calculations you make, the evaluation of f that is here, the evaluations for f in this method are the same. So here you evaluate f 4 times, and here you need to evaluate f 5 times. So you might have a method where these evaluations go here. So to compute the 5th order, you only need one more evaluation. And this is good to have these two methods is good because so you have a method that goes like delta t to the 4th, the other delta t to the 5th. And so you have an idea, if you compare these two solutions, you have an idea of the error you are making. And you can correct in a better way. So sometimes you use this.
So that is the RK45.
The name?
Yeah, I mean it's common to use RK45. So is this an invalid operator?
Probably, I don't remember the names. There are some algorithms which have some names, which are 4, 5. If you look here, you can see them. This is a library in Julia which has many methods, all implemented in the same way, so you don't have to worry. You just say I want to use this method and it will produce the solution always in the same way. The end result will be similar. You can use it later, so this is very convenient. So here I discuss a bit something we saw the other day, yesterday. So how to do with systems. Huh? So suppose you have a spring with a mass, and then this spring has a constant k, Hooke constant k. So Newton's law will tell you that the acceleration is proportional to the force, which is linear. And so you have this system, right? And this is second order. So how do you solve this problem? Well, we know that for solving this problem, physically you need to give the initial position of the mass and the velocity. And suppose you want to solve it with some position, initial position, and zero velocity. Huh? So this is equal to 0, say. But you can say, okay, this is second order. There are some methods that work with second order equations, but the easy way is to make this system first order, to use the library, say. So this, to do it first order, what you do, I have problems. As we did the other day, is just to define the velocity and then take the time derivative of the velocity, which is just acceleration equal to the Newton. And so if we take the second derivative of x, so another derivative here is a derivative here, and so you get it. Right? So it's equivalent. So you write down the system as a vector, a two-dimensional vector, with components x and b, and the force, the F also write as a vector. In this case is a vector b minus kx, and so you obtain a system, right? And so this you can plug into the algorithm. the algorithm all work with vectors, so it's okay. So what we did here is to look at the geometrical interpretation. Remember that an ordinary differential equation is a vector, is vector f, and what you are looking are the integral curves, the y's such that the velocity of the curve is equal to f, to vector f. So what we did is to plot this thing in a plot and also the curve solution. And what you get if you do that is this in here. Right, so this is a curve. This is a curve with start with some, I don't know, I think was x0 equal to 1 and b0 equal to 0. And we follow and you see that this curve follows the vector. The vector is tangent. These, by the way, are examples on how to draw vectors in a plot. Here for Julia, you use something which is called, what it is? Use this function arrow. This function arrow, which is the definition, will plot arrows. So then we use to plot the arrows everywhere. Because you want to plot the arrow, the line, and then the head of the arrow in a way that is, if this vector is small, the head is also small. It's very messy, but you can use it. Now you know. So remember we can have a non-autonomous systems. So if we have a system like that, we discussed this yesterday. If we have a system like this, then you write it as a bigger system with a y and lambda and have this like this. The vector is like that. This I have to correct this. And so for this you have to give boundary conditions, not only initial conditions, not only the y vector initially, but also the value for lambda t0, and we just take t0. And so this way we can just, if you have a non-autonomous system, you can put this in the library and that's it. Or actually in the library they provide for f of y and t. And in general they provide things for functions with some parameters. So you have some parameters here. So you can change the parameters and change the functions. And so just write something once and you can use for several things. So this exercise is an exercise of, if you have we have the Runge-Kutta here, fourth, here, where it was, this Runge-Kutta here, that doesn't have any time. There is no time here. So how do you produce a Runge-Kutta with time? And from the trick of this trick, you can see what happens. And what happens is that you have a K1 with this lambda n. You have K1 lambda, the component for the lambda component this. And so when you write down the K2, you say omega n plus K1 and lambda plus K1 lambda, etc. And this here, since K1 lambda is delta t times 1, is lambda n plus delta t. This is for the, I think this is for the Hoym. Yeah, this is for Hoym. And so you see the lambda n plus 1, as it should be, is just lambda n plus delta t. And the W is like that, and the way the time enter is this way here, and this. So here you see that you have the full step. So when you write down the full system with the time included, is omega n times plus K1, delta n, Tn plus delta t, and this way. And you go marching with this algorithm. So from one you can get the other, very easy. And I think that there is an exercise here to do it with Runge-Kutta 4 here. So you do the same. Do the algorithm here with delta t. This already have the delta t here. So you go to 1/2, again to 1/2, and then to full step. And you can get this one doing this sort of calculation with the previous one. So now we are going to see error propagation. The theory of the error propagation is very important because you need to know what is going on, and in practice is really important because we are going to, it allows us to see what the errors are you're doing, whether your method is conversion or not. So now we are going to discuss the error propagation, and only for one-step method, because for our purposes we are always going to use in the codes one-step methods, namely Runge-Kutta 4 or Euler. So we have this equation, and we want to approximate with a one-step method. And remember, at the end of the day, the one-step method is Bn plus 1 is equal to Bn plus something that depends only on Bn and delta t. Right? This is a last step in the Runge-Kutta, and you build this A doing all the intermediate step. For Euler, this A of B is just f of Bn. For the mean point is this one. For Hoym is this one. So this is the evaluation at the midpoint, and this is the average from the previous point and the vector field at an approximation to the second point. So all the Runge-Kuttas and the Taylor's methods are of this type. You only use, all what we are saying here is that we are using Bn only and delta t to compute Bn plus 1. That's why they're called one step. Whatever the algorithm is, can be very complicated here, but that's all we need. So we are going to now to express the error for this general scheme. So you define the truncation error or the residual, and this is, notice that we have divided here by delta t. So this residual is, here you put the exact solution and you do this approximation, right? So UNM plus 1 minus UN delta t minus this thing. So this will be, for the approximate solution will be 0, but here we are taking the exact solution and do this residual. That is what is error if we put the real solution in this formula. So this here we can compute up to some order using Taylor's expansion. So we say this is, we span in Taylor's series this point, this is this u here, right, is u at t n plus 1, which is u at t plus delta t. So we express this as u in t plus all the series, the Taylor series terms. So you get that this is u dot plus second derivative delta t over 2 plus third derivative delta t squared over 6 and so on. And now we use equation. So every time we see a u dot, we replace by f. If we have a u double dot, this is f dot of f dot in u, and this you write down as a partial derivative of f with respect to u times u dot, and this again is f of u times f, and so on. So when you do this calculation, you get this line here. So this one is this one here, and this is the second order. So you have two derivatives of f times f squared, and then you have one derivative of f with respect to u squared times f. So you have 3f and two derivatives. And so on. So now we can rewrite the error. For the method. For instance, for the Euler's equation, the A is just f of u, you get this in here. And you see, this thing you can replace by these terms in the Taylor expansion, minus f of u, so you get this thing, and the error is linear, delta t. Right, so this is the error. The truncation error is proportional to delta t times these things. For the midpoint, you do the same calculation. You replace, this is the midpoint, the A for the midpoint. You replace this by the Taylor series. And this one, you do Taylor expansion of f, so that will be f1 plus the time derivative times this, so, and this is the second term. And then you have you go to second order in the Taylor expansion of f. You have this other term here, delta tq, and you can write down all the delta t goes away, and you get this thing, a term like delta t squared. So it's the truncation order for this method is second order. And this is the expression for the error, the leading order of the error. And you can check all this thing is the same that we had before. The one parameter family of second order systems. And here you can compute the truncation error for the Runge-Kutta, which is this one, and the Runge-Kutta force is this algorithm, right? So you have to substitute here this f, this f, this f. So take Taylor expansion of all these f's around delta t equal to Bn, and you will get the error. And this is basically the same exercise we have above, so it's the same. So now we want to study how the error propagates, because that is going to tell us something very important about the error. So we define yet another error, which is this En. This is the error. Look, this is the difference between the exact solution and the approximation divided by delta t to the p. So we are thinking that the error is going to be of order delta t to the p. So this is for some a to the p. Something we know already, the error is the local error, truncation error is order p. So from the truncation error, we get this line here should be some error. We know this formula, we know it depends on the u or Tn times delta t to the p plus 1 plus higher orders. And this remainder is a function of u at Tn. So, and on the other hand, we have the expression, the algorithm to compute things, where here is the approximation. So we can take this minus this to get that the error at the step n plus 1 is equal to the error at step n plus this term, which is the a at u here from here and the a at b from here, divided by delta t to the p plus the error, everything times delta t. So since this part we can use Taylor's series expansion. Since we know that this minus this is order delta t to the p for the error in the previous steps, the En. So we just do Taylor series expansion here. So this is going to be around, say, this point. So this is going to be the derivative, right? Derivative of A with respect to u times En that comes from here times delta t to the p from here. The difference between these two is En times delta t to the p. So when we do that, we get this expression here. Okay? So the error satisfies this. This is the same thing, where we have evaluated here at delta t equal to 0 because what? Or we can approximate this function that depends on delta t here, put delta t equal to 0 here, right? Because we already have a delta t here, so if we do Taylor expansion around delta t, there will be one which is 0 here, and the next term will be delta t squared, so we can put it here in the error. So what we get is this is equivalent to this relation, where we have here delta t equal to 0. Now all these steps when you take delta t equal to 0 are just f. this thing here is f of u at Tn. So this is the derivative of f at u equal to Tn. So you can think of this, you can say, okay, the error is evolving like a Euler approximation to this equation, right? If you have this equation, this will be the Euler approximation, right? Because here you have this is the f. So it's something that has a phi here, linear in phi, and some terms that doesn't depend on phi. And this doesn't depend on delta t, it's just a function. And furthermore, as I say, this derivative of a with respect to u is just f of u, right? So we can substitute here by f. Is it clear? Okay. So we have the following assertion. If f of u is smooth, and given you note there exists a time interval for which the solution exists, and the approximation to it given by a scheme of order p has the form ut, which is the exact solution, is the approximation plus t to the p times some function phi of t that satisfies this equation. And it's a function of t, right, which through this f of u depends on u, on the exact solution. But for our purpose, it's just a function of t. Doesn't depend on delta t, only on u and f. Right, so we get this relation. For instance, if you take f of u to be lambda times u, then this equation here will be just the same equation, right? Because if you take the derivative of f of u lambda for times u, this will be phi dot equals to lambda phi plus r. So that will be the, so if this lambda is real and growing, the error is going to grow. If lambda is imaginary, this will tend to go around, but it will have a growth because this term, and so on. So this is how it works. If lambda is decaying, also the solution will be decaying, but at the end will be dominated by this term. Remember, this term is some derivative of, further derivative of f. Yeah.
So this works near the start point, right? You said that there's an interval between 0 and t.
Yeah.
But you can ensure that for long periods the error will be of the other p, because the other terms of larger order may be greater, right?
Yeah. They could become big. There will be, but if you take delta t smaller, they will become smaller, unless the f is not smooth. But if the f is smooth, the remainder is controlled. It's something that you know that is there and it scales like that. It's something finite. I mean, the solution can, that doesn't tell you much, because suppose you are having a solution which is growing exponentially very fast. Okay, you say I multiply this by delta t, still is very big. Yeah, you imagine you are using delta t 1 over 100, and your solution is 10 million, so still is very big. So when you have growing things, the error will grow exponentially, because that's this says, for instance, if lambda is bigger than 0, right, this term, I erase it. So for this thing is, if dot is lambda phi plus r, if lambda is positive, this is going to grow. But the solution also is growing.
But
Right.
for a longer time, I don't know what is the order of p plus 1 on that residual, right?
Yeah.
It could be something like phi squared.
Yeah.
And if phi grows exponentially, then that term may become larger.
Which one? This doesn't have phi.
Oh, it can be related to.
This depends on u and f and
Yeah, of
derivatives.
course. But it can grow like larger than phi, right?
If grows, if you have a solution that is growing, yes. I mean, remember that we can solve y dot equal to y squared, and this exists for a finite time. So when you try to solve that equation with the Runge-Kutta, it will be bad after a while. The error will be big
So
because
can you estimate the time t for which this error estimation works?
no, what you do in practice is something else. We will see now.
Okay.
So because to compute these things, you need to know the solutions, and you don't know. You might say, okay, I have many times what you do is to study solutions near some solution. And if you are doing that, then you can, maybe you know some solution and you are studying the solutions nearby. When you do that, then this controls everything. But in general, if you say, okay, I want to solve, who knows? But there is a way of controlling the error, we'll see now. And that is something we use every day. Because what we want to see, as you said, we want to be in the regime where this thing holds, right? We want to be in the regime where this thing holds, and this thing is small. So, how you do that? And this is a next step. What you do is the following. You take a solution with some delta t step, and then you take with delta t 1/2. So you do a solution with you have a solution Bn with step 1, which here I should put 1 to be more clear. And then you do another one with 1/2. So you solve twice the problem. And suppose you have the solution, UTN. I think, yeah, here this 2 is wrong. Let me change now. It should be 1. Where was it? Here. So we take here a solution Bn and Bn 1/2. So this is one at the same Tn. Here I put 2n because since we are taking this time step half, I have to go twice. So it's the same point. It's same for is the value that would correspond to Tn, this one and the n. And so the theory tells me that this goes like this, and this goes like that. This is the same phi, and the error is different, but doesn't matter. And here you have delta t to the p, and here you have delta t to the over 2 to the p. So if you do the difference between these two and these two, you get a delta t to the p here by phi, and here a delta t over 2 to the p, right? And this phi is the same, so you cancel them, and you get 2 to the p. For instance, if your method is fourth order, this is 2 to the 4, right? 2 to the 4 is what? 2, 4, 8, 16. So for Runge-Kutta 4, this number should be 16. Okay? So if you get this number when you do the calculation, then you know that this term is small, because we threw it away here. So if you get something different from 16, it's because this term is small. Sometimes you will get something too big, and that's because the phi is near a 0, and then this cancellation doesn't work very well. So sometimes you get 16, and sometimes you get something like that, and if it is not conversion, you get something. Right? But you should get 16. And then you are sure that this term is small. Okay? But for doing that, you need to compute to know the solution, because I have subtracting the exact solution from this. And in general, you don't know. So you can do something else. And let me tell you what. You can compute now a solution with Bn, with h delta t. We can compute delta t with delta t over 2 and with delta t over 4. Right, so we have this one here is now we do the difference between this and this one. And so we subtract from the one above, we subtract this from this. So you get this one here on one side and this on the other, okay? Because this minus this is 0, this part is 0. So you equal this to this. So you get this relation, that this difference goes like that. So if you now take the other two, these two, and subtract them, so you do Bn 1/2 minus B2n 1/4, you will get an expression like this, but now with delta t over p divided by 2. Delta t divided by 2 to the p. So when you do this number now becomes 2 to the p also. And for that you don't need an exact solution, you need to compute 3 times the solution with different resolutions. Okay? So in practice what we do is this. When people say, well, we study conversions, is to study this. You take four runs with different resolutions, you do this quotient, and you should get 3 runs. This one, and this one. and you compute this Q, and this should be 16. And this we are going to do in the labs all the time, because that way you make sure that you are in the convergence region of your method, so that the error behaves like we say. The error behaves like this, with this smaller. Actually, you can characterize more this. You can do the error of the error and get that this is another function that depends only on t, etc., to delta t to the p plus 1 and so on. But doesn't matter. The important thing is that now you can control the error. You have this Q, okay? But this allows, suppose you computed the V1 and V1 half. So you have this in here. So you computed this one, this approximation, and this one. You can check that this V twiddle, which is 1 over 2 to the p minus 1 times this factor here, is an approximation which is better. Goes to the 2 to delta t to the p plus 1. Why? Because if you do this subtraction here, this is an exercise, but basically what it says, you can get this one. So you see here there is a difference. So I can, instead of taking this approximation and this approximation, I can make a linear combination of these two such that this term is 0. Oh, I guess there is some problem with the net. No, not here. Let me stop the recording. We have some problems. Well, nobody can hear. Okay. I don't know when, up to what point could you hear? No? Oh. No. hear me? Seems to be back. Let's see if I can share the screen. Oh, 1 second, I will have to go upstairs because I cannot share the screen. So we continue now. I don't know at what point it was close, but we were, when I realized this, I was here, and I was telling that if you look at these two expressions, you can subtract one from the other with the weight so that you cancel this term. So you multiply this by 2 to the p and subtract from this, right? So you will get b1 1/2, and this cancels, minus 2 to the p b1, and then this is going to be u times 1 minus, 2 to the p 1 minus 2 to the p, right? This equal to this, so u is equal to 1 minus 2 to the p times b1/2 minus 2 to the p b1, something like this, has an error which is bigger because they cancel this, and so the error of this approximation is order delta t to the p plus 1. So this combination is more precise. So this is called extrapolation. And this is what it says here. So you should check, this is the exercise, check that you get this extrapolation. So if you are doing calculations all the time using two refinements, you can use this. Se cortó de nuevo.